What if we want to implement a more complicated desugaring this way? For example, we have the case notation, where the intent is that you dispatch on the value of this expression. If it's equal to this number, you return this expression, and so on. If you don't find a match, then you evaluate this last expression. So if we have case plus 1, 2, whether it's 3 or 4 or something else, if it's 3, we'll return the symbol 3, and of course it will be. But the way that we can interpret this expression is by desugaring it into lets and if zeros. And let, of course, will desugar itself, but we don't have to worry about that desugaring. Along the same lines, actually, this is more work than we need to do necessarily. This is a big rearrangement of all of these pieces, and we could have any number of cases. So in the spirit of using pieces that will be further desugared, we could change the case form into evaluate the expression, handle the first case, and then push all the rest of the cases down into another case form, which could be expanded later. So if we do things this way, then we just have 4 different chunks that we have to rearrange into this other piece. And it's always 4 different chunks, so we don't have to do any sort of unbounded processing of any number of cases. Well, it's always 4 pieces in this case. What if we have just case x else? In that case, it should expand to just a let of x. We can do this just to make sure that x is evaluated, kind of encoding of begin, and then just return the body. So in this other possibility for case, we have just 2 pieces to rearrange. And the way we know whether we're in the 4-piece case or the 2-piece case is whether the keyword else is the first in the beginning of the first clause here. So according to our grammar, we always have any number of these things followed by one else. To implement case desugaring as a function, it'll look something like this then. So here I've got case, which takes an S expression. It makes sure that the first of the first clause, which is the third part of our S expression, is a symbol, and that symbol is equal to else. And if so, then you're in the 2-piece case, otherwise you're in the 4-piece case. Right? And notice that in the 4-piece case, we end up generating a new case form that uses that recurs with all the rest of the clauses, which is the rest of the rest of the rest of S. So for example, if we use case on case x else no, that's the simple case here, because this is the first, second, third of the outer S. This is the first of that. That is a symbol and is equal to else. So we'll use this part here, and we'll get this result out. In the more complicated case, this is not an else right here, and so we use the other piece. Now I'm still using back quote and unquote here. You can simplify this all down to conses, and the same here, right? And we'll see that expansion later, but this is enough to give you the idea. So again, it's showing how we can take a complicated piece of sugar, like case, and ultimately be able to implement it in something that's pretty similar to our curly brace language. We have to sort out the if and the and here, and somehow turn it into if zero and add suitable symbol predicates, but those are pretty straightforward additions to our interpreter. It's going to take us a little while to get there though. Before we do that, we're going to go back and look at sugar the way we've been adding it at the PLAI typed level.